Okay, thank you. So now we are starting our official meeting. I don't believe. All right, so welcome to our General Assembly meeting. And this is Friday, November 18th. We have our welcome. We have a little current business to do after our Salapalooza here. And then our featured speaker is going to be via Zoom because she's getting over a cold, as some other folks are tonight. Dr. Maitrayee Bose, and I apologize if I'm destroying that name. Do we have any visitors tonight? No? Yes, I know we have some visitors from far away. How far away are you? Okay, and you've come to the right place. People here actually do speak kilometers. So can you introduce yourself? Or Tom will?
So the host kid at Tom's house about 12 years ago.
Okay, great. So we're glad you're here. Hope you're having fun. So tonight, Claude Haynes, I'm your president. VP is open. Secretary Gordon Rosner in the back taking notes. Treasurer Alex up to her neck in sales related things. Our board, stand up or wave: Dave Kosho, John Kester, Bill Peters, Brooke Schofield, Derek Youngson. And I think everybody's pretty much here tonight. So James Yoder is our property director. Great round of applause to James for selecting all of this stuff over here and kind of organizing all of the equipment. We do get quite a bit of stuff over the course of the year. And Alex is in the back, our events coordinator, and Marty is somewhere here. There's Marty, our webmaster and newsletter editor. So for tonight, that was supposed to be a single slide, but anyway. So tonight is election of officers. So these are the nominees. We are available to take other nominations if somebody wants to run, but we have a full slate. Any other nominations? I'm running again for re-election as a second term, so I will be term limited next time. Woody has volunteered, and I think he's covering tonight at the observatory, so Don could be here for a minute. Has agreed to be vice president. Secretary is James Yoder. Treasurer is Brooke Schofield. Don Wrigley in the back has agreed to a one-year term, and it's because of the way the bylaws are written. We have 1 year and 2 year terms to kind of offset, and because Brooks is resigning, that gives us an uneven number, so we will have a short term for Don. And then the 2 year terms are Tom Mosden, Steve Bradshaw, Alex Beck. Steve, I know you're here. Tom is up front. You can wave so people know where you are. Steve is over in the second row there, and Alex Beck is on the Zoom call tonight. He had some family activities tonight and was not able to join us. Do I have a motion from the floor to accept our nominees for 2023? Dave Douglas as a motion. Do I have a second? Bill has a second. All right, all in favor say aye.
Aye.
Any opposed? Thank you. Now, I want to thank you for all of the people who have volunteered. I especially want to thank Alex, who is in the back. She is now a full-time student at ASU and has decided that full-time studenthood is a lot busier than she thought it would be. So she's kind of stepping away from things this year. And I really want to thank John Kester, Bill Peters, and Derek Youngson for being board members for an extended period of time, because their 2 year term was during COVID. And so things kind of morphed into 3 years. And I really do appreciate their time. So please, round of applause. Now, I want to talk about something that you may have seen in some emails. If you have subscribed to Arizona Observing, or many of you are also members of EVAC and the Saguaro Astronomy Club, They held their elections at the last meeting, and Tom Curry was term limited as president, and no one volunteered to be president or other officers. I think Jack Jones might be continuing on as treasurer. But SAC is in a very poor state at that point if they do not have officers. So I first want to encourage you, if you are members of SAC or you know of people who are members of SAC, and that they can help to keep the club. Saguaro Astronomy Club, thank you. Saguaro Astronomy Club on the west side of town. If you have friends who are members of their club and can encourage them to help step in to take a role as an officer or board member, it would be greatly appreciated. SAC has been, Joe, how long has SAC been around? 45 years? About 45. Okay, so it's been around a really long time. It has a wonderful history with Steve and all sorts of people who did observing lists early on. And so I think it's just with sadness that Saguaro is having some issues, but it's with joy that I'm looking at so many faces here tonight, so many people who participated in the sale, so many people who are on the Zoom call. I really, really do appreciate all of the people who have helped make EVAC successful, because that sort of thing is not done by officers or board members. It's really done by you, the members, in supporting our activities, in supporting our star parties, in supporting the observatory. All of the things that we do, that takes place because of our volunteers and our members. So I want to thank you for that. Moving on, upcoming events. Alex has been our events coordinator, but also because of the time commitment for school, she is stepping away. We are searching for someone to help us with event coordination. If you are at all interested in that, please contact me. It's a very important role. Unfortunately, after the pandemonium, we're kind of rebuilding our efforts. So in the past, we would do 45 school star parties a year. Right now, we have maybe 10 scheduled so far. And so we need some help with that if we can, if anybody is interested in helping us with the coordination of our outreach. Or volunteering for the observatory. It's, I think, closed by now because the clouds are rolling in. I'm not big on fake news, but I do believe in fake weather. And I'm looking at my app and it's clear. It's supposed to be clear in Gilbert. No, sorry, not. So the weather permitting hits us again. I do want to talk about something that comes up in December, Riparian After Dark. This is a special event of the town of Gilbert. It takes place from December 9th through the 20th. It is it's Zoo Lights Light, okay? It's half the crowd, but also probably half the displays that you have for Zoo Lights. But it's very pleasant. You walk around, there'll be hot chocolate vendors, there'll be musical groups. It's a holiday tradition here in Gilbert, but it is a paid event. So this year now it's $2 if you're buying a ticket through December 8th. It's $5 the night through the 20th. As a ticketed event, we don't have public viewing, but the observatory will be open on Friday and Saturday nights for our regular schedule, or the people who are participating in Riparian After Dark. That means that our second Friday Skywatch party and our regular meeting, which falls within that 12-day period, we aren't having. And the primary reason is the parking lot is full. This building is sort of locked. They have portable toilets outside. And so it's just not conducive for us holding our meetings. And so for the second Friday Star Party or our regular meeting night, no. But we have on Thursday, December 22nd, our 35th anniversary party. Join us, join us for a catered meal, Italian. We will supply coffee and iced tea and water. If you want something a little more medicinal or spirited, bring it yourself. The dress code is ugly Christmas sweater casual. But it would help if you would RSVP to me to let us know how many people are coming. It is for members and their spouses or their families if you're a family member. But we do want you to come and join us and celebrate 35 years of some fun things. We will have some trivia questions. We'll have some door prizes. Some of them could be things you see on the corners of the room. So come and join us for a fun time. And that is basically our business. Anything else, Gordon, anybody, Brooks, anything I have left out? Okay, there. All right, so without further ado, Maitrayee Bose, and I'm sure she will correct my pronunciation, and I apologize. She is at ASU, a cosmochemist and a laboratory astrophysicist. I'm not sure what she puts on our IRS form, but I don't think it has quite enough space for that. But we are delighted to have her here. Last month we talked about meteorites and the meteorite collection that we're starting to build for the observatory. And she is the one who is going to analyze all sorts of things and tell us their chemistry. So we welcome you tonight. And I'm going to stop sharing my screen. And if you will start sharing yours.
Perfect. Good. Well, thank you. Thank you so much, Tom, for inviting me to give this talk on sample return missions and my association with them. I'm sorry to not be able to be there in person. I really did want to come there, but I'm recovering from a cold. And while I'm giving my talk, I might pause and you might see me go, mute and come back. I'll come back. I'm feeling a lot better, but if I talk continuously for a very long time, then I tend to cough a little bit. Anyway, so my name is Maitrayee Bose. I'm an assistant professor in the School of Earth and Space Exploration at ASU. And thank you again for inviting me to give this talk. I have in my collection dust grains that have been captured by several different missions now, and I'm going to share some of that data with you. But before I go into what I work on, I wanted to give a very quick overview of asteroids, meteorites in general. And I know that you all know quite a bit about observing them, whether it's through your tiny telescopes or through these talks that you all have about where experts come in and they give talks about different things. And so I'll start with this image of the night sky, looking to, into the very dark night sky, looking at stars, of course, the galaxies that you might observe, but also the planets, right, in our solar system. So we have all these major planets kind of in one single snapshot like that, which to me is very, very cute and exciting at the same time. I do study stardust that are also found in meteorites, but I will actually not talk about stardust today at all, just focusing more on what we have been working on in getting samples back from asteroids. So I will not talk about stardust, but I can in the future if need be. So when we look at the night sky, you're looking at these shiny objects, and then you look at the planets, which are also obviously shiny, and we don't quickly realize it, or at least I was, when I realized it, that a lot of these objects are rocky. They're made of silicate minerals. They're made of these rocks. And if you actually start learning about them, you realize that a lot of these rocks actually have compositions that are similar to terrestrial rocks, to rocks that are found on Earth, Earth's mantle, for example, right? So there's so much similarity, and we have all these rocks floating around us. And of course, a lot of these rocks then fall on Earth, right? And so this is just two examples. One in 2013 that I'm sure you all have seen videos of Chelyabinsk, which is a very massive boloid that fell in Russia into one of these ice lakes and broke up into several different pieces. And this is just a picture of one of that one of the big pieces. ASU actually has several of these fine pieces in its collection. So if you ever visit ASU, you should go to the area where we actually showcase some of these meteorites, and you'll see a bunch of these Chelyabinsk rocks in it. And on the right, I'm showing a picture of a very recent meteorite that fell in UK in Winchcombe, which is actually making a lot of news. I'm sure there was a article in Science that came out today, I think. And so there was this huge splash in BBC and all the news outlets about it, where they found this very, very dark piece out pretty much on the grasslands. And so, you know, a huge team of scientists from UK alone measured all sorts of different things in this meteorite to figure out what it is made up of and why does it have the composition it does. And it's a very, very carbon-rich, organic-rich meteorite compared to this one, which is more rocky or has more iron metal in it. So for Chelyabinsk and for several other objects, we have been able to figure out from what angle they were falling in the sky. And then from that model, where this particular rock may have come from. And so I'm showing you a picture where it's like, okay, this is the kind of modeling people do to figure out the trajectories and the velocities with which these bodies were falling. A lot of times you can imagine that the rock itself can get hot enough and they might explode. That's something that happened for Chelyabinsk, for example, right? So, and it's not just like one time, it can happen several times before some of the pieces come and fall on the surface of Earth. In any case, you can backtrack this trajectory to figure out where exactly they came from. And for Chelyabinsk, this is this blue, it's not exactly circular, but elliptical ellipse that you can see that. So this particular, the asteroid parent body of Chelyabinsk moves between the orbit of Earth and Mars, right? So it has an elliptical orbit and it moves in and out as it goes around the sun, right? So this kind of work can be done, and maybe some of you already do this, I don't know. But this is the kind of work that several of the groups around the US are trying to do so that they can, once they see a flash and it's reported, you can actually go and collect some of these samples. So based on some of these kinds of models, we know very well, and of course we have lots and lots of telescope data. We know where the asteroid parent bodies are in our solar system, right? So these are just very basic figures that I took from a textbook from which we know that there's a huge population of these asteroids between Mars and Jupiter, right? But of course we have a lot of others, such as you have the Trojan asteroids, which are orbiting in the orbit of Jupiter, only in front or behind Jupiter itself. And there's going to be a mission that is going to go visit 8 different Trojan asteroids. Okay, so if you've heard of the Lucy mission, that's what the Lucy mission is going to do: take close-up images and do spectroscopy of some of these Trojan asteroids. But of course, also I'm showing you asteroids that Ceres, which is actually an asteroid and a dwarf planet. It's one of these very unique objects that is both. It's a very, very ice-rich asteroid, and it's an enigma actually as to how it formed. Vesta is an asteroid that we've been to. We actually have meteorites from Vesta or from the Vestoid family in our collection as well. Okay, so the very, very interesting asteroids that I pointed out in here. So of course we have lots of small bodies between Mars and Jupiter. And as you can imagine, these bodies, yes, they're going around the sun, but as they are going around the sun, they're pulled and pushed in various directions by all the different planets, and especially Jupiter being around, right? And you keep moving them inward, okay? So what happens is you can see, you can see a few of them really, really close to the orbit of Mars, and you can imagine if you come inside the orbit of Mars, you still see a lot of these objects there, right? So these are the near-Earth asteroids that are very easily accessible to us. Like if we want to go visit an asteroid, we will choose from some of these, and that's what we have done so far. Of course, apart from the main belt, we have lots of small bodies in the Kuiper belt. And we know that there should be a huge number of these asteroids beyond the orbit of Neptune. But we actually don't have a very good estimate of the total mass. Okay, and this is something that hopefully JWST will help us estimate. JWST is a telescope that I'm sure you all have heard about now, where it measures with infrared spectroscopy and at infrared wavelengths, not just galaxies and stars and exoplanets that are forming around stars, but also the small bodies in our own solar system. A lot of these bodies are extremely dark, and therefore seeing them in optical wavelengths is very, very hard. Whereas in infrared wavelengths, they just are these bright specks of dust. And that's what people want to do with this telescope. So hopefully, with JWST, we'll be able to figure out what populations are out there in this Kuiper belt. So these are where the source regions of the meteorites are, right? And of course, these, as I was saying, the near-Earth asteroids, they come to, basically they're being accreted by sun, right? So they're moving inward, and they fall on not just Earth, but also Mars. So here's a picture of iron meteorite, and we named it Lebanon, that was found on the surface of Mars by the Curiosity rover. And I find this really, really cute that we are finding meteorites not just in our deserts, in whether you go to Antarctica or the Sahara. So not just in the hot and cold deserts on Earth, but also on Mars. And of course, the speculation is that it's not just iron meteorites that fall, but all sorts of meteorites fall, but only those meteorites that can survive the very, very intense radiation and any kind of intense temperatures will be dominated on the surface, and that's what you see these iron meteorites. We also have enough evidence of meteorites falling on Jupiter. So this is in 1994 when I was in high school. Essentially, Shoemaker-Levy made this big splash where there's this string of impacts that were observed by telescopes. And this particular comet had been torn apart into several different pieces, and we could see these impacts at night, like this picture that's showing here with the glow of the impacts. But also later on, we saw effects of it in the atmosphere. And that's something that was even more clearly seen in this particular impact, 2009, where we actually didn't really see the object striking Jupiter, but we did see the scar that it left. Okay, so these objects are continuously bombarding the inner solar system. Solar system bodies, but the inner solar system planets, including Earth. And we have been able to do flybys to a lot of these asteroid bodies, and we have a general sense of how they look. So here is just a collage of different asteroid bodies. And so, I have the names in there, but it's a little tricky to see. But there are small ones, that is 2 to half a kilometer size bodies like Hartley. And then you have the massive ones. You have ones with a binary, like a satellite with it, right? So this is IDA with its satellite dactyl. And one common thing is, of course, they're all non-round, right? Non-spherical in shape, right? So it's just various shape, potato shape, or whatever you want to call it. So that's one thing. And second is, of course, all of them are very small, and they are very, very dark. They're pretty hard to observe in optical wavelengths. The other thing that people observed when they did flybys of some of these bodies was the surfaces are heavily cratered. right? So lots and lots of evidence of cratering, as you can see in Ida and also in this particular asteroid. And the surfaces often do not contain very fine-grained material. It looks like they have these big boulders on them, okay? And so, this is kind of interesting because you would have expected that if a body is heavily cratered, you would sort of have more of the fine-grained dust on it, right? Which was not observed. And so then a lot, with say 20 or 30 flybys, we started to figure out how they looked, whether they had a satellite or a moon of itself, or whether they were just two objects of similar sizes going around each other. So you had asteroids that are, binary asteroids, as they call it, which is a significant fraction of these asteroids. And then we started speculating, the community started speculating whether these are one solid, single monolithic bodies. Yes, they are made up of rocks, but what is, how consolidated are they? How compacted are they? Okay, and in terms of just looking at the pictures, you always feel, oh, they have to be one single compact body, right? It was very difficult to envision how a non-compact body that's loosely held together would look like. And so, our initial thinking before all these missions were so common was that it's, most of them are these solid rocky bodies with lots of cratering. Pretty much think of a planet, just make it small, but otherwise everything is the same, kind of a thing. Okay. We did find some asteroids that look just weird and wacky. So this is a picture of Orokoth, where it's a contact binary. So we had essentially two pieces or two lobes that was going around each other, and at some point they were stuck to each other, right? They impacted each other at this neck and they got stuck. And one of the things that we discovered is, of course, it may produce this really odd shape, but also the two lobes were not spherical to start with. One was spherical, but the other was more like a pancake, right? So you had this weird shaped objects that would get into orbit with each other and create such unique, exotic, weird shapes, right? So this is one of the big questions that we had. And with the missions, we've been able to kind of answer that question really well, that asteroids are not really like planets at all, in terms of how consolidated the material is. Loosely they're called, yes, they're rubble piles, okay? And simulations have shown that if you have an asteroid, suppose you blow up an asteroid into its smaller fragments, whether it's boulders, meter-sized boulders, or even smaller particles. Smaller particles you would eject from the system completely, but the bigger boulders, you would actually put them together. And this putting back together into these objects, right, can be done in a week to a month. So they're very, very, very quick, okay? So then the question is, as they're coming together, how much of a compaction or lithification is happening? And now that we have visited these three asteroids, and I'm going to talk about the missions a little bit, but these are the three asteroids that we have visited and we have samples from. And I'm going to talk about the missions a little bit. But just studying them, we now know that each of these asteroids is filled with air. It's like 50% air by volume. Okay, so these really fluffy, porous materials, they're just barely holding on to each other. Okay, that's the kind of objects these are. And to think of it, the material from these objects are as old as our solar system's age. So it's 4.568 billion years old. And so they have been like this for a very, very, very long time. Okay, some of them may have gotten, were impacted multiple times. So there's some evidence of that from grain measurements, but they always came back, they always reformed, maybe slightly smaller because they lost some material, right? And of course, the other thing is the shape. The shape clearly indicates that something special is happening with these particular asteroids. Okay, so in terms of, trying to connect asteroids to meteorites, right? What kind of characteristics do we see in meteorites? Well, we see, very generally speaking, two kinds. One that's highly primitive, one that which we think formed very, very early in the solar system history, and has not really changed much. That those bodies, those asteroid bodies, never really got heated much, that stuff in it melted. If you have melting of rocks, then you would actually start to produce other rock compositions. And that's what I mean by processed. And try to figure out their compositions. How much water did they come with? That's one of the big science questions that I try to answer. Because the general theory of planet formation, there's several scenarios. One of the scenarios is that you can have tons of these primitive asteroids, the ones that have never been altered. They have collided with each other and accreted to form our planets. Our planet, but also all the solar system planets that we know. So if we want to know, the process of planet formation, or what starting materials formed our Earth, then we need to know what these primitive meteors look like, and then go from there. So just some very basic stuff about primitive meteorites. If you take one of these rocks and you do a section through one of these primitive meteorites, what do you see? Well, we see a lot of shiny metal, metal grains, iron, nickel, sulfur-bearing materials. But also a lot of these rocks are extremely dark. So if you can see the very dark, you see a lot of very round objects, right? I'm pointing to this particular one, but there are lots of round objects. Those are the chondrules. Those are silicate melt drops that are incorporated in the meteorites. You'll find lots of white stuff like this one and this one, maybe this one too, like the edge of it. Those are called calcium aluminum rich inclusions. And those are the first solids that have formed in our solar system. And in between, just holding the calcium aluminum inclusions and the chondrules, is this very dark matrix. It's made of a very, very fine grained material. And that is pretty much rich in organics. So any carbon, nitrogen, phosphorus bearing material. And so for my research, I look at a lot of these areas, looking for very, very pristine organics. What's the characteristics of the organic materials that are there? So that's something that I try to investigate. Now, I was talking about, you have the primitive meteorites and the processed meteorites. Now, when we look at all the different meteorites that we have in our collection, so this is a pie chart from Johnson Space Center. Give me one. Okay, so this is a pie chart from Johnson Space Center website, and it's showing all the different very primitive meteorites that we've identified so far. Okay, so they're called chondrites. Never mind the name. But essentially what you're seeing is we have large numbers of this L, H, and LL chondrites. And these are, we call them as ordinary because they are so, then they're commonly available. Every other rock that falls from the sky, if you look at it, the highest chance that these are these particular rocks. And so they're not very special. They have lots of silicate minerals in them, lots of iron in them. I guess if people like metal. So yeah, lots of metal in them in general. And so that's, the biggest section of this pie chart, right? The smaller section are these, which are Cs, CB, CH, CK, CM, COs, CVs. that C stands for carbonaceous chondrites. So these are these that are really carbon rich, phosphorus rich meteorites. And there's this whole field that's trying to explore whether life on Earth was initiated by meteorites. And in order to do those studies, they have to look at these section of meteorites, the carbon-bearing carbonaceous chondrites. So these are the ones that are the most primitive, and I'm showing you the distribution. But what about the processed meteorites? So yes, we have a large number of very processed meteorites. So let's start with this green one. So you have the howardite, eucrite, and diogenite. So remember I was telling you that we have been to this asteroid Vesta, and we actually did not know when we were going to visit Vesta that we already had meteorites in our collection that actually came from those asteroid bodies. So it was pretty revealing. Oh wait, that we were going to this mission and to find asteroid to sort of map Vesta, but we already had meteorites. I'm going to stop for 1 minute. I need to check by my laptop is not getting charged. So give me 1 second here. Okay, okay, I'm back. Sorry about that. So we have meteorites from Vesta-like asteroids, which are these HEDs, right? We have lunar meteorites, right? It's a pretty large section there. Martian meteorites, tiny fraction there, right? Uralites are really, really special. They are asteroids that were large enough that differentiation happened. So you have formation of the crust, mantle, and core, but they were the first planetoids that formed. So imagine we having a piece of such a body, the ones that have formed really, really early on in the history of our solar system in our labs, and being able to understand what the composition is and what it's telling us, right, about the process of planet formation. Anyway, so I just wanted to show you that there's a slew of different kinds of objects that existed, throughout our solar system history, and they've probably been transformed, or who knows, right? And we wouldn't know that till we actually go sample some of these bodies. And so I was talking about near-Earth asteroids, and just a schematic showing the closest and the biggest asteroid flybys of 2022. So, you have all these asteroids streaming in, and these are just the ones that are the really big ones. The flyby distance is given in yellow, in million kilometers. So, for 5 million kilometers, 2 million kilometers was this one in January, right? So you had them come, and the closest was about 0.8, which is the orbit of Moon. So it's not really very close to Earth, as you can tell. But suppose we decided to go visit some of these asteroids. It would be perfect if we can identify them, right? And so there is a very classy mission, in my view, called a Neowise Surveyor, which is going to be launched, I think, in 2026. And it is supposed to map every near-Earth asteroid that's greater than about 100 meters or so, so that if any of these asteroids are coming towards Earth, we'll actually know it, right? We know its orbit very well, and therefore we can sort of track it, which I think is very, very cool. We can, if we know where they are, we can go visit them, right? And that's pretty much how Itokawa was chosen. So going to the first mission, that actually visited an asteroid and brought back samples from it was a Japanese mission. So JAXA is the space agency. And they basically planned the Hayabusa mission to this asteroid Itokawa. This is one of these close-up pictures showing that this object is also a contact binary, where you had two lobes that were going around each other and at some point collided, right, and made the shape. The weird part was, before we went to Itokawa, we didn't think that its surface would be covered with so many boulders, because you saw pictures of the collage of asteroid pictures that I showed you, and all of them have very smooth surfaces. So landing on a smooth surface to do sample collection is going to be trivial, right? But here we had a ton of boulders on the surface and only a very small neck area, which was smooth enough that we could actually go sample, which is what they did. They sampled in two places, and the samples were brought back. And this is just a picture in the Australian desert, where they're basically collecting the sample container. Of course, you can imagine it has a heat shield, right? It's landing, so you need a heat shield to make sure that the container doesn't get hot, and the sample container is in the heart of this little unit. And when they opened the containers, what they found is the container was pretty much empty. So this is the aluminum container. You can see a few particles floating around here, but that's it, okay? And that was mainly because the mechanism by which they were going to capture samples from Itokawa's surface actually did not work. So they had originally planned that there would be this horn that would slowly move to the sample surface and touch the sample surface, while there would be this ball, this metal ball that will be dropped. And that would stir up the material and would get into the horn and get collected. The ball was never released. So there was some failure at some level. And so the horn did touch, and whatever particles was collected was as a result of that, right? So you have some of this material just electrostatically charged floating around that got captured. Now, the Japanese scientists were pretty smart in that they discovered that although particles were not really collected in abundance, right, they were able to see particles that had gotten stuck on the metal itself. So this is just a picture where they're looking at, basically they flattened out the entire container, and you're looking to see if you can find any dust grains in there. And of course, they found lots of artifacts, right? The blue ones are showing the artifacts that are not Itokawa particles. But then they started finding minerals. And then once they had them, they started doing analysis on them, and they realized very quickly that those are not contamination particles. They are not defects in the container itself, but they're actually particles from the surface of Itokawa. And so I think now they've been able to identify about 2,000 particles just by doing this, which to me is amazing. Here's some high resolution pictures of these particles from Itokawa. And I have on the right, I have just written down the mineral names and the composition so that you can kind of see what they're made up of. But they're, olivines, pyroxenes, chromites, troilites, all these different phases that we actually find on Earth, right? So nothing different, but their isotopic compositions are very unique, okay? And that's something that a lot of people have worked on. And based on very detailed characterization, we've been able to figure out what asteroid Itokawa's history looked like. So we can imagine that initially this asteroid was pretty big, big, more than 20 kilometers in size, and it was in the main belt, okay? And then because of its size and the fact that it had aluminum-26, which is a radiogenic isotope, it would convert to magnesium-26 with a half-life, and it would start to heat this body. So it would go through this period of thermal metamorphism. And then it actually went through a catastrophic impact. Remember these two little lobes, right? It's a contact binary. So you somehow have to create that shape So you would need an impact that would create large boulders, which would then reaccumulate and form this rubble pile that we were looking at. And then after it becomes a rubble pile, the processing of the materials doesn't stop because you have a radiation environment there, right? You have constantly photons and high energy particles that are bombarding the surface of the asteroid. And so you do see effects of the solar wind interacting with the particles, or you see regolith formation because of grinding effects and so on. So we pretty much figured out what, how, the entire history of Itokawa, right? That's one thing, but also the timings of it, okay? How old is this object? And when was the catastrophic impact? Was it just once or more than once? Things like that, right? So there's like hundreds of investigators doing analysis of different things, from the noble gases to the light isotopes to major elements and so on. Now, one of the questions that we wanted to answer at ASU was, is Itokawa dry and desiccated? So, they are silicate minerals. They have been bombarded by, it's coming closer to the sun, so it's getting heated in general. It's also bombarded by high energy particles. So, what are the effects of it, right, is what we try to answer. And so we, at ASU, I have a lab that has this very, it's a fancy instrument. It's a more than $5.5 million instrument now. It's called the NanoSEMS. And with the NanoSEMS, we can measure water contents in different minerals. And so the objective of this work was to measure water contents and also the hydrogen isotopes. So hydrogen has two stable isotopes, hydrogen and deuterium. There's also tritium, but we can't measure it. And so we decided to measure hydrogen in two different mineral types, and we knew where the hydrogen would be for these minerals. And when we met after this, so this is a plot I made after we measured. It's a slightly more complicated plot, but I want to go through it a little bit, where on the x-axis, I'm showing the water contents in parts per million, or if you want to convert it into weight percent, that's 0.1 weight percent is 1000 ppm. And on the y-axis, what I'm plotting is delta D values, which is calculated as the ratio D over H normalized to a standard, okay? And for our case, the standard is SMO, which is standard mean ocean water. And so any value that has a delta D value that is negative, like here, right, it's considered D poor or hydrogen rich. And if it has a positive value, then it is D rich or hydrogen poor. And for the Itokawa particles, we found that they are actually D poor in nature. And it fell right where we know Earth's water and Earth's rocks lie. So this blue rectangle that I'm showing you of bulk silicate Earth, that is the composition range of all of the terrestrial minerals and water. Right? And pretty much Itokawa was like right there, right? So you have this asteroid that's formed in the main belt, right? But has the exact same water characteristics as Earth. And so then what we did was try to understand if some of these particles that we had measured had somehow been altered in a way, or you added water to it, or you lost water to it. So all the different processes that would either lead to production of water or hydrogen or loss. We had to sort of model and figure out how much that would be. And then we estimated how much water some of these Itokawa-like bodies have. And so Itokawa, we said, was like between 160 to 510 ppm, or 0.2 to 0.5 weight percent water. And with various calculations and models, we said that if you have Itokawa-like bodies that are trying to form a planet like Earth, it can give us at least half of Earth's oceans. Okay, so this was very, very interesting and new, at least at the time that we did this. This is some time ago now. But it sort of showed that this whole theory that people have about planets forming from smaller asteroids that might actually be true because they have enough water in them that when you start forming a planet from them, you're already creating a planet that's hydrated in itself. So that was very cool. I'm going to stop here for a moment to see if anyone has any questions.
There is one question.
Okay.
I thought most asteroids, no, most meteorites that are on Earth, the water content of the isotopes doesn't match that of the water on Earth, and neither do comets. So that asteroids and comets seem to be a poor source for Earth water. Can you comment?
Right. So that's a good question. And I don't have a plot here to show you, but there are a section of of meteorites that does have some overlap with terrestrial water. Comets are a different story. Comets are extremely D-rich in nature, and therefore we don't think that the source of water on Earth is from comets per se. But there are a section of meteorites, especially the carbonaceous chondrites, that have some overlap. So as you can imagine, of course, people keep getting new data, but as you can imagine, these ranges are they're quite big, right, for a lot of these meteorites. And unfortunately, I don't have a plot to show you, but I can send it to you if you can email me a plot that shows that there's a pretty big range of water contents for the different meteorite classes, and there's some classes that have overlap. Is that okay? Is there any other question?
No, I think we're good.
Okay, so I'm going to continue, and since I have I don't know 15-20 minutes, I'm going to move on. So Itokawa parent body, we think actually formed in the inner solar system. So if you look at this particular schematic, we have the snow line. So this is this approximate distance from the star, our sun, where you have water that's in the vapor phase or to the left, so closer to the star, right? And then if you cross the snow line, you start to condense out the water into ice pebbles, right? And Itokawa, we think, come from the inner solar system. But what we wanted to know about bodies that formed in the outer solar system, how would they evolve? How would they look? Their bodies would be more water rich, and will they preserve the 4.5 billion year history of the different materials? So that was pretty much the motivation for the next two missions, going to Bennu and Ryugu. Bennu is, of course, a NASA mission that's led by University of Arizona, and Ryugu is another of the JAXA missions that also went to a carbonaceous chondrite. They both look they're very similar in their characteristics. They are both pretty carbon rich, like I said. Their average distances are similar. Their orbital periods are very similar. They're called sister asteroids in some sense. So here are pictures of approach to Ryugu. So this was back in 2018. And then you can see Ryugu from a distance of about 40 kilometers. And one thing that immediately struck people was, again, this whole thing of too many boulders, too many large boulders on the surface. But also the unique shape of it was pretty evident here, where you have this top shape, and people started speculating what would cause such a top shape, what would cause this equatorial ridge that you can kind of see here. And so people started mapping, this particular asteroid in great detail. On the left, I'm showing you all the very large, 8 to 10 meters, right? Very large boulders on the surface, and started figuring out, okay, if we're going to get samples back from this asteroid, where do we land? That was a very complicated question. And they finally found, areas that were safe for landing. These are some of the high resolution images they got. And one of the striking things was they found this very bright whitish material that didn't seem like it was intrinsic to Ryugu. And when they did spectroscopy on some of these rocks, they found that they actually have compositions that look like HEDs. And if I just want to remind you, HEDs are meteorites that we think come from Vesta-like objects. So we have materials impacting Ryugu from other classes of asteroids. They were able to land with these rovers and able to take pictures. Sorry about that. They were able to take pictures, and you can see how rocky a terrain it has, right? And then they decided to do their first touchdown in this area, where this would be marked by a marker that they would place. So these are these metal balls that they dropped, and you can kind of see it there, those balls. And then you would have the horn come down, and and then they would have the same mechanism where they would drop a ball, which would stir up the material that would get collected by this horn. So this first touchdown worked wonderfully. And this is a picture taken after the touchdown, and you can see how dark the material has become, right? For the second touchdown, what they wanted to do was sample the subsurface. So the Hayabusa 2 spacecraft essentially dropped this massive metal ball and created an artificial crater. And so this was, just when the ball was hitting and impacting the surface, it created this plume of material. And you basically found this fresh subsurface material, because the idea was that you would have the surface material being bombarded by particles and seeing lots of space weathering, but the subsurface material would be more pristine, right? And so then they did a second touchdown where they collected some of this material that we think come from the subsurface of the Ryugu. And then the samples were brought back. So this is the same picture I had shown you earlier when Itokawa came back. Oh, the date is 2010. And then this is very recently, 2020. And if you look at the containers now, they're chock full of particles from Ryugu, which is amazing. They brought back about 5.5 grams of rocks, which is a lot. And right now, people are studying these rocks. So we have some particles in my lab right now. And we've learned a lot already from these rocks. We know, again, the surface materials are extremely weak. They have between 40 to 55% porosity, which is, it's extremely porous material. The boulders give you the illusion that they are boulders, but they're actually just loosely stuck particles. It's very easy to actually destroy some of these boulders, is what people are speculating right now. Based on the mineralogy and detailed isotopic work, we know that they come from, or they're identical to the CI carbonaceous class of meteorites. We do have some in our collection so we can sort of do comparisons with. So, we're learning a lot, but we've just started to work on these samples. So I want to move on to the next mission, which is NASA's OSIRIS-REx mission to asteroid Bennu. And again, this is going to closest approach, finding Bennu. This is how it looks. And we were a little surprised that it looks identical to Ryugu, but it's actually much smaller than Ryugu. Well, not much, a little smaller than Ryugu. And this is a mosaic of the highest resolution image that has been acquired for Bennu, which is amazing. You can see the craters in there. Of course, you see big boulders sticking out, right? But the team had the same problem where they were not sure where they're going to land finally, because the entire surface is like full of these large objects that look like boulders. Of course, you can see lots of color variations too, which is saying something about the mineralogy, or the variable mineralogy that you can see on the surface directly. Right? So people speculate, okay, where is the fine-grained material which makes up a lot of these meteorites? And that's a big question that we all of us in the community are thinking about right now. Is it that these asteroids have enough movement due to impacts that you have the fine-grained material trickling inward? So you have all the rocks exposed, like in the desert, for example, right? If you have wind blowing in and it sort of removes the fine-grained material, exposing some of these bigger rocks. Is that the kind of process that's happening? So this is something that all of us are discussing right now. And just to indicate, these are pretty large boulders on the surface. Right? One of the things that was really interesting for Bennu was we saw this plume of particles that were ejected from the surface. And we were able to, the spacecraft was unaffected by this because they were observed early on. But essentially, we think what's happening is you have this, this asteroid spinning up and spinning down, and that results in ejection of some of these particles over time. And of course, a lot of them are reaccreted. So on top of these boulders, we find these particles, these fresh particles again, but some of them are probably lost to space. And then we were able to find, oh, this doesn't look right, but yeah, we were able to find an area to land. And so they did the same kind of landing where you would have the horn go and touch the sample surface. The way in which they would stir up the material in this case is slightly different. So NASA decided, well, the team decided that they would push air through the surface, like sort of like pressurized air. And that would stir up the material and would take them into the collectors. And that's what they did. And it was highly successful in collecting samples. So successful that a lot of the particles that were collected, so basically you're looking at the sample head, there are these metal Velcro pads that are supposed to collect more particles as it's doing the touchdown. But then once the air comes out, stuff will go in, and this metal ring is essentially chock full, like a tire, right? Chock full of particles. It was so full that it was actually not completely closed. So you can see this ring, the sort of the rubber ring that would keep the particles from coming out. It was actually bulging, right? So they had to very quickly stow away this collector so that they don't lose any more particles and they can bring back more than what they had asked for. So, it was stored away very quickly because we had captured so much samples and said goodbye, and it's on its way to Earth. And hopefully we'll have a ton of material to work with. Samples come back in 2023. So this is my second last slide, just showing you pictures of, these amazing samples that we have from these two missions, highly successful in my view. And this is just me. I went to Stanford to do some synchrotron measurements to understand organosulfurs, so sulfur-bearing organic materials. And this is on the right, a picture of the Ryugu particle that's been allocated to me. And this is the particle that we're trying to study. So I'm going to stop there and take questions.
Okay, we'll pass the microphone for questions.
When Lucy gets to the metallic asteroid,
Would you expect it to be a rubble pile, or would that be something more solid and more compact?
Such a good question. I don't know. I really want to say that we actually don't know. It's been a bizarre series of explorations for us, where the first initial flybys we always saw more solid monolithic bodies. And then suddenly now we've been to three. All three are rubble piles. So it's kind of hard to tell what we will see. In my view, we should see more of rubble piles. I think they're more common in our solar system. Also, because of the interactions, if you have a collection of asteroids, the chances of them interacting with each other gravitationally, or the chances of impacts might be more, for all you know. So if the impacts are more, we'll have more rubble piles. So yeah, I mean, we don't know yet. I think it might most likely will be rubble piles, but we'll have to see. That's a good question.
Dr. Bose, what's the current thinking on what holds the asteroid together and the boulders together? Is it just gravity or electrostatic or some sort of chemical glue?
Yeah, so it's not gravity. I mean, yes, it's very, yes, it's gravitationally attracted, but it's a very low gravity field, right? So it's a lot of adhesion. So adhesive forces, capillary forces, van der Waals forces, so all electrostatic forces. So there's definitely some amount of charging. All those together somehow keeping these particles together into these units. So one of the things that the OSIRIS team had talked about just after touchdown was that the touchdown event is actually very slow. They move about, I don't know, 1 or 2 centimeters every hour or something like that. So it's extremely slow, but it's kind of automated, because once they know where they want to land, they just move it, right, very slowly. When they knew that they had touched the surface, right, they had not actually told the software to stop moving down. And essentially, this particular cone head went a meter down because we didn't tell it to stop. And so they were saying how porous the material is, that the collector didn't feel any kind of resistance at all. And the team had to fire thrusters so that the collector device would actually start to move up. So
That's amazing.
Yes. So they were like, if we hadn't started the thrusters, I'm sure we would just go in deeper. Of course, they couldn't afford to do that. But.
Wanted to ask you about you were measuring the water in parts per million. Now, is that
Yes.
By mass, or is that by molecule?
It's by mass.
Okay, thank you.
Sure.
Okay, one more.
Sure.
Oh, 2 questions. One is, what is the distance of the ice or the freeze zone from the sun?
You can imagine it's not like one value, right? Because of various reasons. Pretty much between 2 and 2.5 AU would be a good distance to kind of.
The second question is, for meteorites that enter Earth's atmosphere, when they're in space near Earth before they arrive, what is their internal temperature before they hit Earth?
Very cold, ice. So it depends
Thank
on
you.
the size a little bit, but you can totally expect a gradient of some kind. In fact, even after they enter through the atmosphere, a lot of meteorite collectors have said that when they actually go and touch the meteorite, the stone is actually not hot. It's not melted. It's not hot. In fact, it feels cool to touch, which to me says that the internal temperature of some of these small rocks, they are pretty cold. Maybe not ice at that point, but cool. Great questions. Wow.
Okay, another one coming up.
Yes, you mentioned that the probe didn't encounter any resistance when it landed on the surface. Could it have actually gone all the way through and come out the other side, you think?
So this is something that the ORIX team thought could happen. That they would actually break apart, or they could very easily break apart a small body. Maybe not that particular body, maybe not Bennu, but some of these asteroids that are even smaller, and we try to sample it, we might actually end up disintegrating them.
Any last questions? Oh, here we go.
Do we know about the object that NASA recently crashed into about a month ago?
The DART mission?
Yeah, the one that probably really made a mess of that one.
No, actually. So they're, of course, they are, they had a small probe that went at really high speeds. And of course, the amount of destruction you would create or you could create depends on the material properties, right? And whether it is really a monolithic body or a rubber pile, right? So for those bodies, I know that they were able to change the spin rate, and it has produced craters, but no data has been published yet on it. Plus, it is a like a defense mission, not a full-fledged NASA mission. So we actually may not even see a lot of the data that comes out of that particular mission. I know a couple of my friends are involved with the DART mission, and they've been talking about papers, but no data has been shared with the community or with the public yet. And we don't know what section will be. So we'll may not know for a very long time what happened to those asteroids or to that asteroid.
This is Tom. I've got another question. So the observatory has a meteorite collection, and as the visitors come up to the telescope to have a look, they can look at the meteorites too. Do you know if there's somebody at ASU we could talk to help us like expand what we would need to do to expand that collection, or, you know, just tips?
Yeah, so one of the things I was thinking about was you should, I don't know who among you are involved or want to be involved, but if you email the director or get an appointment with the director, I think that would be better, and talk about having specific meteorites curated for a period of time at your observatory. Mm-hmm. I think that might be really cool, because then you have this relationship with the center. And this is something that actually BCMS, like the Center for Meteorite Studies, we actually do that, where we get meteorites from other places, from the Natural History Museum or some other museum, and we actually keep it in our collection for 6 months or 3 months, like, you know, some period of time. And we display it and we talk about it and stuff like that. So if you can create a relationship between ASU, the BCMS, and this observatory, then having these, you know, curated pieces appear would be, in my view, would be really good. I was thinking about it a lot, Tom, after I saw your email. So you could contact the director directly, and if you CC me, I can sort of be a liaison. I can, you know, I would love to be a part of this new thing that you want to try, whether it is to collect meteorites. So that's the other thing. The curator of BCMS, he has done a lot of meteorite collections around in Arizona. So if there's a meteorite fall, he comes to know. He's actually been there to collect samples and stuff. So if that's something some of the members would be interested in doing, you have to let them know that, okay, we are interested in doing something like this and stuff like that. But I don't know what's the interest, what's your interest level? So,
Okay, is that Devin, or is that a new person?
No, Lawrence Garvey is the one who has been to.
Oh, Lawrence.
Yeah.
Okay.
Yeah, he's the one he's the curator actually.
Yeah, I know Lawrence too. Well, I don't know Lawrence. I've seen him on TV.
So yeah, I can introduce you to him if you're the one who's going to talk to him about it.
Okay, yeah.
But I feel like the other option where you would have, say, we always have this meteorite of the month or something. So something like that, where you can take one meteorite and you can, or a couple of meteorites, and you display it in your observation for 6 months or 2 months or something, and then you return it. And that sort of helps you. So you don't have to worry about storing them or, other factors with it, with the money and everything, but you still
Right.
have a collection to show.
Okay, thank you. Yeah, that's a good lead. I think that's the last question. Yes. Let's thank our speaker again.
Thank you so much. And apologies for stopping so many times.
Thank you again. We really had a pleasure with your talk, and we appreciate your time. Hopefully your cold does well. So thank you again. We will see you when? In December? Thursday, December 22nd, not our regular meeting night. Come and have a fun time with our party. Be sure to check the Observer, be sure to RSVP, and we'll see you then. Thank you.